Well, hello. So this is going to be chapter 5, the standard deviation as a ruler and the normal model. So I'm going to just record a short video. We're not going to cover the entire chapter. We'll finish this on Monday or Tuesday, depending upon when your class is. All right, so let's get started here. And I'm going to present this. Okay. So we have the next slide. In this chapter, we're basically going to understand shifting or rescaling data. We're going to be able to standardize data, and we're going to use the 68, 95, 99.7 rule to understand distributions. And then finally, we're going to check the nearly normal condition. So the standard deviation is rulers. The trick in comparing very different looking values is to use standard deviations as our rulers. The standard deviation tells us how the whole collection of values varies, so it's a natural ruler for comparing an individual to a group. As the most common measure of variation, the standard deviation plays a crucial role in how we look at data. So when we compare individual data values to their mean, relative to their standard deviation, we use the following formula. Z equals the quantity y minus y bar over S. So what that says is we're going to take each data value, that's what the y stands for, okay, and we're going to subtract the mean of the data set, and we're going to divide by the standard deviation. This z is called a z-score, okay, and it's also a process called standardizing the values. So the cool thing about standardizing the data is that standardized values have no units. So that allows us to compare apples to oranges. When I have two different data sets, if I want to see how they relate to one another, the best way to do that is by standardizing because it gets rid of the units. Z-scores measure the distance of each data value from the mean in units of standard deviations. So that's very much like a ruler. If you notice on a ruler, there have units like inches or centimeters. Well, in statistics, we have a similar ruler, but this time our units are standard deviations. So a negative z-score tells us that the data value is below the mean, while a positive z-score tells us that the data value is above the mean. If we've got a z-score of 0, that means it was the mean value. So benefits of standardizing. Standardized values have been converted from their original units to the standard statistical unit of a standard deviation from the mean. Thus, we can compare values that are measured on different scales with different units or from different populations. So now we can compare females to males. And now we can compare pounds to kilograms. Okay? So for z-scores, it is hard to underestimate the power of usefulness of standardized scores. We will calculate them in this course on countless of occasions, especially in the final 3 units of this class. All right, so we're going to try example 1. Okay, cars currently sold in the United States have an average of 135 horsepower, which is standard deviation of 40. We want to calculate the z-score for a specific car with 195 horsepower. All right, so let me go to my, let's see here. I want notability, and we're going to also bring up the calculator. All right. So I'm just going to identify my values from this problem. I have to get my pen going here. All right, here we go. Okay. So the first thing we notice is we have an average of 135 horsepower. So in my formula, that is y bar. Okay. With the standard deviation of 40, that's my S. And we have a z-score. We want to calculate a z-score for a specific car with 195. So that's my y. So the formula is z equals y minus y bar over S. And I plug that in, and I'm going to get 195 minus 135 over 40, which is going to give me 60 over 40, which is going to give me 1.5. So my z-score equals 1.5, and there's no units with z-score. So what that really says is the number 1.5 is 1.5 standard deviations above the mean. All right. And let's go back to my situation here. Okay, so present. Okay, so next concept, shifting data. Adding or subtracting a constant amount to each value just adds or subtracts the same constant from or to the mean. This is true for the median and other measures of position. In general, adding a constant to every data value adds the same constant to measures of center and percentiles, but will leave measures of spread unchanged. So in the following distribution, or histogram, shows a shift from men's actual weights in kilograms to pounds, okay, or vice versa. So if you notice, switching units don't actually change by adding or subtracting 75 units. You get the same distribution, the centers are the same, it just moves, shift over a little bit, and the spreads are identical. Okay. So what is the center of the two distributions? Well, on the left-hand side, the center looks to be around, I don't know, 70 kilograms, and on the right, the center looks to be around, I don't know, 0. Okay, and then the IQRs, we can subtract Q1 and Q3, Q1 and Q3, and find the IQRs. Now, when we divide or multiply all the data values by any constant value, all measures of positions, such as the mean, median, and percentiles, and measures of spread, such as the range, IQR, and standard deviation, will be divided and multiplied by the same constant value. So, if I'm adding and subtracting, the only thing that's changing are measures of center. When I'm multiplying or dividing, measures of center and measures of spread will change by the same operation. So as you notice here, if I multiply everything by 2.2, my centers changed and my spread changed. Okay? So let's try example 2. So suppose a class took a 40-point quiz. Results show a mean score of 30, median 32, IQR 8, standard deviation of 6, minimum of 12, and Q1 of 27. Suppose you got a 35 on this. What will happen to each of the statistics if I decided to weight the quiz as 50 points and will add 10 points to every score? Okay, so your score is now a 45. Or if I decided to weight the quiz as 80 points and double each score, your score is now 70. And if I count the quiz as 100 points, I'll double your score and add 20. So let's see what happens to all of my measures. Okay. All right, so let's go back to Notability. Bring my calculator back up in case I need it. Okay, so here's example 2. All right, so basically what I'm going to do, okay, is write my original values here. Okay, so we have the mean, we have the median, we have the IQR, we have the standard deviation, we have the minimum, okay, we have Q1, and we have your score. All right, so in my original amount, the mean was 30, the median was 32, IQR is 8, standard deviation is 6, the minimum is 12, Q1 is 27, and then your score was a 35. Okay, so in the first situation, I'm going to add 10 points. So what that does is it changes measures of center, but does not affect measures of spread. So my mean will become 40. I just simply add 10. My median will become 42. My IQR stays the same. My standard deviation stays the same. My minimum moves to 22. My Q1 moves to 37. And my score moved to 45. So measures of position or center here will be added, but measures of spread do not change. Okay, so now what if I decided to double each score? So everything changes in that situation because I'm multiplying. So my new mean becomes 60. My median becomes 64. My IQR becomes 16. My standard deviation becomes 12. My minimum becomes 24. my Q1 becomes 54, and my score becomes a 70. All right. Now, what happens if I double? So 2 times and add 20. All right, so the 20 is only going to affect measures of position, and the 2 times affects everything. So for 30, I'm going to multiply by 2 and add 20. I'm going to get 80. For 32, I multiply by 2 and add 20. I get 84. My IQR, I only multiply by 2. My standard deviation, I only multiply by 2. My minimum, I'm going to multiply by 2 and add 20. So I get 44. My Q1, I multiply by 2 and add 20, and I get 74. And my score, I multiply by 2 and add 20. All right. And let's go back. Okay, so now let's go back to z-scores. So standardizing data into z-scores shifts the data by subtracting the mean and rescales the values by dividing by their standard deviation. So when we standardize into z-scores, it does not change the shape of the distribution. Standardizing z-scores changes the center by making the mean 0, and in standardizing it changes the spread by making the standard deviation 1. Okay, so when is a z-score considered big? A z-score gives us an indication of how unusual a value is because it tells us how far it is from the mean. So a data value that sits right at the mean has a z-score of 0, where a z-score of 1 means that the data value is 1 standard deviation above the mean, and a z-score of -1 means that the data value is 1 standard deviation below the mean. So how far from 0 does a z-score have to be interesting or unusual? So here's the hint. There is no universal standard, but the larger a z-score, the more negative or positive, the more unusual it is. Often, we consider a z-score greater than 2 or less than 2 to be roughly an indication of unusualness. But every data set is different, so we need to be careful. So generally, if data values are within 2 standard deviations, that's good. Outside of 2, they're slightly unusual. Outside of 3 standard deviations, it's basically really unusual, okay? And then, of course, higher than 3, so 4 or more would be extremely unusual. Okay. Remember that a negative z-score tells us that the data value is below the mean, while a positive z-score tells us that the data value is above the mean. If you forget which order to subtract, use common sense. Is the value above or below? Should I have a positive answer or a negative answer? So let's do example 3. So let's talk about scoring the decathlon. A silly example, but suppose 2 competitors tie in each of the first 8 events. In a 9th event, the high jump, one clears the bar 1 inch higher than the 1,500 meter run, and in the 1,500 meter run, one runs 5 seconds faster. We have to be able to compare 2 fundamentally different activities involving different units. Standard deviations to the rescue. If we knew the mean performance by world-class athletes in each event and a standard deviation, we could compute how far each was from the mean in standard deviation units called z-scores. So here's the problem. Consider 3 athletes' performances shown below in a 3-event competition. Note that each place first, second, and third in an event. So who would get the overall gold medal and who turned the most remarkable performance in the competition? Okay, so let's go back to Notability and Calculator just in case. All right, so what we're going to do first, okay, and I'm going to kind of model what we're doing here. So step 1, I want to think, okay? So remember, this is the first step, think. So we want to compare athletic performance across several different events. So we need some way to compare without units. We will compare z-scores from each event. Also, don't forget that lower times are better in the 100-meter dash. Okay, now we're going to go on to our show step, and that's where we calculate. Okay, so we need to find z-scores. All right, so we're going to first find them for the 100-meter dash. Then we're going to find it for the shot put. And then we're going to find it for the long jump. All right, here's A. All right, so for A, they got a 10.1 meter dash minus the mean of 10 divided by the standard deviation of 0.2. And I get 0.5, but remember, it's reversed, so we want negative 0.5. So it's actually below the mean because it's reversed. Okay. For competitor B, they did 9.9 minus 10 over 0.2, and I'm going to change the sign when I get that answer, and I get 0.5. And then for competitor C, they got a 10.3 minus a 10 divided by 0.2, which equals negative 1.5. All right, now for the shot put. So competitor A got a 66 feet minus the average of 60 divided by the standard deviation of 3, and I get 2. Competitor B did a 60 minus the mean of 60 divided by a standard deviation of 3, and I get 0. And then competitor C got a 63 minus 60 over 3, and that gives me a 1. All right, so for the long jump, we calculated the z-scores. So we had 26 minus the mean of 26 divided by a standard deviation of 6. Be careful here, right? That's 6 inches. So that should be divided by 0.5. Everything else is in feet. Okay, so that's going to give me 0. The next competitor here is going to be 27 minus 26 divided by 0.5, and that gives me 2. And then I have 27.3, so 27 and 3/12 minus 26 over 0.5, and that's going to give me 2.5. Okay, so I'm going to bring this thing down. Okay, and I'm going to write my tail, excuse me. So B was the winner with a total of 2.5 standard deviations above the mean performance. C came in second and A in third with 2.0 and 1.5 standard deviations above the mean, respectively. And C's long jump was the most startling feat. 2.5 standard deviations longer than average. All right, and let's come back and let's present. All right. So there is no universal standard for z-scores, but there is a model that shows up over and over again in statistics. This model is called a normal model. You may have heard of it as it's a bell-shaped curve. So normal models are appropriate for distributions whose shapes are unimodal and roughly symmetric. So there is a key word, unimodal and roughly symmetric. These distributions provide a measure of how extreme a z-score is. So there is a normal model for every possible combination of a mean and standard deviation. We will write n of mu comma sigma to represent a normal model with a mean of mu and a standard deviation of sigma. So those are Greek letters. We use Greek letters because this means a standard deviation are not numerical summaries of the data. Because this mean and standard deviation is not a numerical summary. They are part of a model. They don't come from data. They are numbers that are chose to help specify a model. Such numbers are called parameters of the model. So summaries of data like sample mean and standard deviation we write with Latin letters. Such summaries are called statistics. When we standardize the normal data, we still call the standardized value a z-score and we write the following formula. So z equals y minus mu over sigma, or a data value minus the population mean over the population standard deviation. Once we have standardized, we need only one model. N of 0, 1 model is called a standard normal model, also known as the standard normal distribution. Be careful. Don't use the normal model for just any data set, since standardizing does not change the shape of the distribution. It only can be used for unimodal and roughly symmetric data. So when we use the normal model, we are assuming the distribution is normal. We cannot check this assumption in practice, so we will check the following condition, the nearly normal condition. The shape of the data distribution must be unimodal and symmetric. This condition can be checked with a histogram or a normal probability plot. So normal models give us an idea of how extreme a value is by telling us how likely it is to find one that far from the mean. We can find these numbers precisely, but it's useful to begin with a simple rule that tells us a lot about the normal model. It turns out that the normal model, about 68% of the data fall within one standard deviation of the mean, about 95% of the values fall within 2 standard deviations of the mean, and about 99.7% of the values fall within 3 standard deviations of the mean. So the following shows us that 68, 95, 99.7 rule. So here's the graph, and we notice that between 1 standard deviation, 68% of the data, between 2 standard deviations, 95% of the data, and between 3 standard deviations, 99.7% of the data. Some textbooks call this the empirical rule. Our textbook calls this 68, 95, 99.7 rule. So let's go to example 4. We're going to sketch a normal model using the 68, 95, 99.7 rule of the following. All right, let's go back to my Notability. Okay, and here's example 4. All right, so birth weights. What's told to us here is that the mean mu is 7.6 and my standard deviation sigma is 1.3. Okay, so we're going to go ahead and draw that. All right, and I'm just going to use this situation here. Let me go ahead and move these down. Okay, so here is a normal model. It looks like a bell-shaped curve. All right. And then we're going to model it. So step 1, we put the mean. Okay. So here is 7.6. Now this is 1 unit of standard deviation. So I'm going to add 1.3. So I have 7.6 plus 1.3, and I get 8.9, and that is the next unit here. Then I add another unit of standard deviation, 1.3, and that's going to give me 10.2. And then I add one more unit of standard deviation, 1.3, and I get 11.5. Okay, now I do the same thing but going in the reverse direction. So 1.6 minus 1.3, and that gives me 6.3. I again subtract another unit of standard deviation, and that gives me 5. And then I subtract another unit of standard deviation, and that gives me 3.7. So within 1 standard deviation on either side of the mean, I'm going to capture 68% of my data. Within 2 standard deviations of the mean, I'm going to capture 95% of my data. And then within 3 standard deviations of the mean, I'm going to capture 99.7% of the data. And then that is all you have to do there. Okay, so now let's try the second problem there. And we're doing ACT scores with a mean of, so mu equals 21.2, and my standard deviation equals 4.4. So again, we label 21.2 there. I'm going to go up, so 21.2 plus 4.4 equals, and I'm going to put 25.6. I think if I hit enter again, it's going to automatically add. No, it's not. So 21.2 plus 4.4, and that's going to equal, add 4.4 again. That's going to give me 30. And then if I add 4.4 again, and that's going to give me 34.4. Now I'm going to subtract, so 21.2 minus 4.4, and that gives me 16.8. I'm going to subtract 4.4, and that gives me 12.4. And I'm going to subtract 4.4, and that gives me 8. All right, so modeling here, we have 68% of data within 1 standard deviation. Within 2, we get 95% of the data, and then within 3, we get 99.7% of the data. And I'm going to stop the video there.